yesterday we discussed the general idea of how position in the periodic table gives us a sense of how tightly held the valence electrons are. All right? And that general idea now today we're just going to apply to some specifics. So those specifics. First thing we do is we divide the periodic table up into two regions. And we put a border between them. So we divide them into metals and nonmetals. And this little redraw of the periodic table doesn't actually appear in your notes. So I apologize for that. But maybe you could very quickly sketch it. So we have the two regions and the border between them, metals versus nonmetals. Where might I find that border that goes between the metals and nonmetals? Adrian? All right, so over here. Starts here and it just makes a staircase going down. Sort of like that. And good point. It also includes hydrogen, so this stairway actually extends all the way over here to hydrogen. So everything up and to the right of that are what we call nonmetals. Everything down and to the left of that dividing line are metals. So everything over here will be nonmetals. Everything down here would be metal. And then the states along the border, those are sometimes called the metalloids or the semi-metals. So right along that border, we have metalloids, which basically means, they're kind of metals, but they're kind of not, depending on which way you look at it. And the biggest distinction here is that metals, they're weak. They have a weak hold on electrons. Nonmetals have a strong hold. It's the biggest difference. And then that explains the properties. So we'll take some time, mostly in the next unit, where we explain how they bond differently based on whether they're metal or non-metal. So very simple distinction you want to make. You want to be able to look at an element and say, well, that element is a metal, that element is a non-metal. If you forget which side of the dividing line is which, try and find something you know is a metal. So what's an element that you know is a metal? Gold. All right, so look, which side of the line is gold on? Oh, it's down here in the middle. Gold would be right over here. You say, oh, I know gold is a metal, so metals must be down there. That means things up here must be non-metal. Well, so the metalloids, some of the things along the border are metalloids and some of them aren't. So for instance, aluminum, we know aluminum is a metal, right? Aluminum does everything that a metal does. So that is right next to the border, but it's definitely a metal. Then you have others that are along the border, like silicon, that we consider metalloids. I'm never really going to ask you to make the distinction. We will, as a first approximation to make things simple, we will try and just call things metals or non-metal, recognizing that there is some gray area in the middle. Okay. All right, so first distinction. Then some other specific properties that we're going to look at. So many elemental properties can be explained based on the number of valence electrons and how strongly attracted to the nucleus they are. Those properties include, and these all come straight out of the the revised AP Chem curriculum. So I just took, all right, what are the ones that they want you to know? We'll list through those. And then there are some others that we used to talk about, or if you took honors chem, you might have talked about things like electron affinity. We won't be talking about that. So you can forget anything you might have learned about that. So they want you to know the typical charge on ions of the element, the ionization energy of an atom, or at least how position on the periodic table relates to ionization energy, the radius of an atom, the radius of an ion, and the electronegativity of an atom. All right. Electronegativity, going forward, electronegativity, if you become a chemist, that's the one that is going to be the most important property for you, is electronegativity. You'll use that term the most. For instance, in the summer I teach organic chemistry. We use the word electronegativity every single day throughout the entire course. So that'll be the most important. But let's just check right through these. Typical charge on ions. So there is a rule of thumb. That we call the octet rule. The octet rule basically says that when elements form stable compounds, they tend to end up with 8 valence electrons. This isn't a fundamental explanation for anything. It's just an observation. This tends to happen. In order to explain it, you kind of have to take it on a case-by-case basis. So we'll explain when things make ionic compounds, why they follow the octet rule, or when things make covalent bonds, why they tend to follow the octet rule. Right now, we're not giving an explanation for it. Right now, we're just stating it. So the other thing you want to know is when they make ions, metals we said are weak. So how do metals tend to make ions? They lose electrons. So metals, which are weak, tend to lose electrons. And nonmetals, which are strong, tend to gain electrons. So if you're a metal and you're going to lose electrons, how can you get to a point where you have 8 valence electrons by losing electrons? All right. So metals tend to lose all their valence electrons, which leaves the next ring down, the next energy level down with 8 valence electrons. So they'll lose all the valence electrons. All right. Nonmetals, if they're going to gain electrons, there it's a little simpler to see how if they have 6, they're going to tend to gain 2 and get up to 8. So for example, if I pick calcium, how many valence electrons does calcium have? Alec? 2. All right. Calcium has 2 valence electrons. Therefore, it's going to lose both of them. And the charge on a calcium ion will be +2. All right. Chlorine, on the other hand, chlorine has how many? Oh, question? Yep. So the question is calcium 2 plus the same as argon? Well, no. Calcium 2 plus, we would say, is isoelectronic with argon, meaning it has the same number of electrons, same electron configuration as argon. But a calcium 2 plus ion is definitely different because it's got 2 more protons in its nucleus than an atom of argon does. So from an electron standpoint, it's got the same number of electrons, but it's definitely not going to behave like argon does. Yeah. So it's an important distinction to say, you know, when you make an ion, okay, it might be isoelectronic with a certain noble gas. That doesn't mean it's exactly the same as that noble gas. All right, so chlorine has how many valence electrons? Luke, 7. So what's it going to do? Gain 1. So it'll have a charge of -1. Right, so you want to be able to use the octet rule to figure out what the typical charge on an ion of an element is. Again, it's not a fundamental explanation. It's a rule of thumb, but if you can use that skill, then you're all set. Maria? So good question. What about elements in column 4? Ignore elements in column 4. It's really hard to gain 4 or to lose 4 electrons. So they tend not to form ions. Yeah, in group 14, at least carbon, silicon. I think on your periodic table they're numbered that way. Oh, they're not even numbered on your periodic table, but column 14 would be the column with carbon, silicon, germanium. Tin and lead can form ions, but they don't follow the octet rule necessarily. So I would just don't worry about carbon, silicon. They're not going to form ions. Yeah, so there are names for a lot of columns in the periodic table. The 18th column, way over on the right, that is the noble gases. Starting from the left, there's the alkali metals and then the alkaline earth metals. Group 17 is called the halogens. Those aren't names that you're going to be tested on, but you may come across them as you read and such. All right, typical ionic charge done. Ionization energy. So this is a specific property. Has a specific definition. We abbreviate it as IE. And that's the amount of energy it takes to remove an electron from that element if it's a gas. So if you have a sample where you've got individual free atoms of that element, how much energy would it take to make an electron pop out? So given what we know about that, given what we know about the general trend, what do you think we can say about the trend in ionization energy? How will that change as you move through the periodic table? As you go down a group, groups are vertical. So that's a piece of terminology worth pointing out. So within the periodic table, columns are called groups, and rows are called periods. So this would be called group 1, group 2, etc. And then rows would be called periods. So the first row would be period 1, second row would be period 2, etc. And you can write that right on your pink periodic table if you want. So as you go down a group, all right, as you go down a group, you're going to higher and higher energy levels, so the valence electrons are further from the nucleus. It takes less energy to remove them. All right. And then as you go left to right, what trend would you expect to see? It'll increase, because as you go left to right, now we said you're in the same energy level, so similar distance, but you're increasing the effective nuclear charge. So similar distance, greater magnitude of charge, there's going to be a stronger force pulling on it. It's going to take more energy to remove. You want to know that trend in ionization energy. Another thing to know about ionization energy is you can measure it more than once. So you can measure first ionization energy, that's the energy to remove one electron. Then second ionization energy would be, all right, if I've already removed one electron, how much energy does it take to remove a second one? And then you have third ionization energy and fourth ionization energy, etc. So you can measure multiple ionization energies for an element, i.e. 1 would be the first electron removed, i.e. 2 would be the second electron removed, etc. So the question is, will we have to find IE? No. You need to know the trend, and if you were shown a graph of ionization energy, you should be able to interpret what that means. But these are values that have been measured. You can look them up. There are tables of them. But yeah, it's not something you need to memorize or know how to find. What do you think happens to subsequent ionization energy? So energy to remove the second electron, would that be easier or harder than removing the first? Take a minute to talk at your table. Decide, is ionization energy 2 going to be greater than ionization energy 1, less than ionization energy 1, or maybe it depends on the atom? All right. So, Ryan, what was the discussion at your table? You think harder to remove a second electron? Why? All right, there's less electron-electron repulsion. If you've already removed one, there's less repulsion, which means there's going to be a stronger attraction overall for that electron to the nucleus. So yeah, you're right. IE2 is always going to be greater than IE1. Because as you remove electrons, you're getting rid of some repulsion, and so what's left is going to be a stronger attraction than there was before. One thing I heard come up, some people were saying, well, for certain elements, second ionization energy might be easier. And again, this is if you're relying on the octet rule as an explanation, as a fundamental explanation, it'll kind of lead you astray. So I overheard some groups saying, well, maybe for an element like magnesium, which has 2 valence electrons, after you remove the first, it becomes easier to remove the second because then it'll have this magic noble gas configuration. It'll have 8 valence electrons. That's not the case. Still takes more energy to remove the second electron from magnesium than it does to remove the first. Getting to that noble gas configuration, that tends to happen, and we will explain why it happens when we talk about bonding, but it's not something that an atom wants to do. It still takes energy to remove an electron from sodium. Sodium would rather keep its electron and be sodium neutral than lose its electron and become sodium plus. It's just, it has such a weak hold on its electron that usually it can't happen to hold on to it because someone else comes along and has enough energy to rip it away. Yeah, poor sodium. So don't try to use the octet rule as an explanation here. Just think in terms of fundamental principles, in terms of attraction and repulsion. You remove electrons, you're getting rid of some of that electron-electron repulsion. It becomes easier to, or harder to remove the second electron. So this is always true. All right, and now, actually, I forget if I gave a slide to draw this in later. If I want to give this argument now. I'll leave it for later, the graphical explanation. All right, atomic radius. So atomic radius is essentially what it sounds like. It's essentially the distance from the nucleus to the outermost electron. That's a little fuzzy because is the electron in a specific place? No. The electron's a cloud, right? So it's really the distance from the nucleus to maybe the average position of the outermost electron, or it could be if you have 2 nuclei and they're bonded, it's half the distance between the 2 nuclei. It can be measured in different ways, but it's essentially the size of the atom. It's a measure of the size of the atom. So since we're talking about a cloud, it's hard to say exactly where the outermost electron is. So you're going to have different ways to define it, different ways to measure it. You don't really need to trouble yourself with that. You just need to know the general trend. If you're thinking about which atoms are going to be biggest, which atoms are going to be smallest. So probably the top to bottom trend is a simpler one to tease out. As you move from the top of the periodic table towards the bottom of the periodic table, what's going to happen to atomic radius? It'll increase. As you move from top to bottom, Electrons are going to higher energy levels. By definition, that means they're further from the nucleus, so the atom's getting bigger. All right, how about from left to right? Atom, you get smaller. Why? Stronger pull on the electrons. The outermost electrons are in the same energy level, but now the attraction to the nucleus is greater. So that energy level as a whole gets pulled in more tightly. So this actually decreases from left to right. So unlike our perception of like strength and size in, say, people, we think of the strongest people as being big and strong. Atoms are kind of the reverse. The strongest atoms are the smallest ones. Right? Fluorine is really small, but also really strong at pulling on electrons. The bigger atoms, tend to be weak, like francium way down there on the left. It's like this big fluffy blob. Um, I like to think of the clouds of the bigger atoms towards the bottom of the periodic table. They're like big and fluffy. The cloud can move around a lot, not held very tightly, shifting from one place to another. Whereas like fluorine has a really compact, almost hard cloud. And that terminology actually comes up not in this course, but if you take future courses, you'll talk about hard and soft acids and bases. And that really has to do with how tightly held the electron cloud is. All right, so that's the trend in atomic radius. Questions there? Awesome. Oh, I didn't even realize I had that. So sorry, I rewrote some of what was already there. I forget I need to take the animations out of the lecture just so that everything appears at once, and then I can write my stuff. Might as well follow the link. It's measured in different ways. I'll show you. If you go to sites and look up, look up sizes of atoms. Here, this is webelements.com. They have no fewer than 1, 2, 3, 4, 5, 6, 7, 8 different ways that you can define the atomic radius of an atom. The atomic radius empirical, atomic radius calculated. So empirical would be based on measurements. Calculated would be based on theoretical values. The covalent radius, so that would be when it's in a covalent bond, molecular single bond, etc. So you've got all these radii. Don't worry about the different definitions. But this site also has a nice visual to show you like the relative sizes. PM is picometers. So picometers are 10 to the negative 12th meters. So you can see a typical bond is about, somewhere on the order of 100 picometers, which would be 0.1 nanometers. So we actually even have another unit. 10 to the negative 10th meters gets called an angstrom because bonds tend to be about 10 to the negative 10th meters in length. So 154 picometers, for example, would be 1.54 angstrom. So if you ever hear the unit angstrom, that's what it means. Oh, good. So the question is, how come there's no pictures down on period 7? I believe the reason is, all those atoms are unstable, and so at least for a lot of them, some of them last for a decent amount of time, like uranium, thorium, etc. So I don't know why they don't have pictures for those, but a lot of those are so unstable, they don't last long enough for you to make the measurement. We kind of ignore all that stuff down at the bottom of the periodic table in this class anyway. We never do anything with it. All right. So then the question about ionic radius. You want to think about what's going to happen to the radius when you form a positive ion. So talk at your table for 20 seconds. What happens? All right, please finish your sentence. All right. Tomorrow, what was the conversation at your table? What do you think happens to the radius when a positive ion's formed? It loses electrons, yep. Loses electrons. Fewer electrons means less repulsion among electrons. They're going to get pulled in closer to the nucleus. So smaller radius when it's positive. Especially if it loses all its valence electrons. Right? If magnesium loses 2 electrons, now you've gotten rid of energy level 3. You're losing that entire outer energy level. You're going to a smaller energy level underneath. All right? Well, I think it's kind of logical when you form a negative ion. You're adding electrons. When you add electrons, what's going to happen? It's going to get bigger. Because when you add electrons now, there's going to be more electron-electron repulsion. So they're going to want to spread out a little more. When they spread out, it means a bigger atom. So when you're comparing the radii of ions, just remember, you can't just look at where it is on the periodic table and say, oh, fluorine is up at the top right of the periodic table, so a fluoride ion is definitely going to be smaller than a sodium ion, which is further down and to the left. That's not actually true, because you have to consider the effect of adding an electron or removing an electron. And that can have a big effect on the radius. Why don't we write that out to be explicit? If you just want to memorize the trend and you say, all right, F further up and to the right, so it's going to be smaller than sodium, you'd be wrong. How do I know that you're wrong? How do I know that F minus is actually bigger than Na plus? Nick? All right, there's more electrons in fluorine. All right, more electrons in fluoride than there are in fluorine in F neutral, and fewer electrons in sodium than there is in Na neutral. There's 2 more protons in Na plus. You consider these, each one has 10 electrons. So the only difference between them is the number of protons. Right? F minus has 9 protons. Na plus has 11 protons. So if you're looking at the same number of electrons, but one of them has more protons, the one with more protons is definitely going to pull the electrons in tighter. So ionic radius isn't something you can just look at the periodic table and just make a a determination right away. You really have to think about number of protons, number of electrons. All right, so that's 4 of our 5. The last thing we got to talk about is electronegativity. And I said electronegativity. I love this word because it's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 letters. How many words in the English language do you know with 17 letters? Not a lot. So that's one cool thing about electronegativity. Essentially, electronegativity is like a composite measure. When you look at ionization energy, that's something you can measure in a lab. It's just a physical number. You measure it. It's this many kilojoules per mole. Same thing with atomic radius. You can measure it in different ways, but it's a physical measurement. I think of electronegativity as the composite of, all right, how strong is this element overall? The analogy I would make, and I apologize to the non-sports fans out there, but when you have, say, the NFL draft, what happens is all these players who want to get drafted and play football in the NFL, they go to this combine, and at this combine, they measure their height and their weight, and they measure how much they can bench press, and they measure how fast they can run. They take all these physical measurements. That's what ionization energy and atomic radius are. They're physical measurements. But then each team has to look at the player and decide, all right, well, how good, given all these different measurements, how good is this player? Electronegativity is how strong is this atom? Given these physical measurements, how strong is it? So it's really an overall measurement of electron pulling strength. And it's defined for electron pulling strength in bonds. Which is why if you look up electronegativity values, you won't find them for helium, neon, and argon, because those 3 elements never actually form any bonds. So that's why you just won't find these values. Just like different teams are going to put different values on each player based on their physical measurements, there are different scales for electronegativity. So just like we saw with atomic radius, you can measure it in different ways. There's the Pauling electronegativity. Linus Pauling was a chemist/physicist. He was the first to use the term electronegativity, so he defined the scale the first time. And what he decided was, I'm going to make the scale go from 0 to 4. And 4 would be the strongest element. So fluorine, he made 4, and then just compared everything else to fluorine on a 0 to 4 scale. So that was kind of arbitrary. All the other scales ended up being 0 to 4 as well, because they were like, well, everyone already recognizes electronegativity as a 0 to 4 scale, so we'll do that. But you see, there's Sanderson, Allred-Rochow, Mulliken-Jaffe, Allen. All these different people came up with different scales. The Pauling one is probably the most common one. So it's on a scale of 0 to 4. And really, the lowest element, I think, is like 0.7. So it's really 0.7 to 4. Well, it's depending on which scale you choose. It might be they're calculated based on, it might be ionization energy and other measured values. So they are mostly calculated based on other measured values, but we don't need to go into like what the measured values are that they use to calculate them. So this is just going to follow the trend that we said earlier. It's going to increase when you go in which direction on the periodic table? To the right and up. All right. So let's just quickly summarize this, put it all on one chart. Essentially, we have two opposite ends of the universe in the periodic table. Those two opposite ends being down here, the francium end, and up there on the top right, the helium end. So for francium, we would say it has, these are going to be the largest atoms. In terms of ionization energy, down there on the lower left, lowest. They're going to have the lowest electronegativity. And they'd be the most metallic. Then on the upper right, we've got smallest and strongest. So smallest, highest ionization energy, highest electronegativity, and least metallic. What I'm going to do is save for tomorrow the graphical explanation. So tomorrow, I'm going to come at this from a different perspective and try and use potential energy graphs to explain this. So we'll call it a day there.